Okay. A little system architecture. You don't need to know this. I'm not going to quiz you over it, but it will definitely help you with understanding what's going on under the hood. We'll, of course, go through this in much more detail in architecture and operating systems. But we can access control files and devices using system calls. The system call is the basic interface from your program into the operating system or the kernel, and the kernel then translates your system call into some way to into the hardware effectively. So you're writing system calls to tell the OS, hey, I need you to print this character, and then the OS figures out what device driver needs to be used and where to put the pixels and which wires to run high, et cetera, et cetera, et cetera. Low functions, yeah, so you open a file, read, write, close, and something called ioctl. Just note that your standard libraries like clib and C++, the STL, they're calling this in the background for you on your behalf. As long as you adhere to the C or C++ interface, you don't have to worry about all these details happening, but it's good to keep it in mind. Let's see, problem with using low-level system calls for input and out, they can be very inefficient because performance penalty on each system call. The other thing that your library calls will do is it'll buffer a bunch of your calls and not actually do the system call until it's absolutely needed or until it thinks it's a good time. That's because every time you do a system call, you're actually changing your user. It's similar to logging out and logging back in because you have to log out as your user, log in as root. Root does its thing, then log back out as root, and then log back in as you. Obviously, they make it way more efficient than that, but you still have that performance penalty. So here, for data structures, this is a good way to think about how your program's running. We'll go into more details later. But your program's running in something called user space. This is you, your user that you're logged into. You have your user program and maybe some library you're using, the STL, clib, OpenGL, et cetera, et cetera. That library or your program will do a system call which jumps into kernel space, aka log out as user, log in as root. System call calls kernel device driver, which then interfaces to the hardware, make sure that the hardware acts the way it's supposed to, and then come back up here, log out as root, log back in as you, effectively is what's going on. Just keep that just in the back of your mind. It'll come up every once in a while. All right, Valgrind. Yes. So Valgrind is a tool to help identify memory errors. Did y'all ever have seg faults in procedural? No? You're going to have them here. So there's a lot of problems with memory. In C++, you have to manage memory yourself. So you have to make sure that you stay within bounds of the memory, and you have to make sure that you allocate the proper amount and that you deallocate the proper amount, otherwise you'll be having memory leaks. What Valgrind is, and I know it's spelled like it should be Valgrind, but it's really pronounced Valgrind. Just that's the way they did it. Debugging memory, leak detection, profiling. It actually runs your program in a virtual machine to figure out what's going on. It is a very helpful tool because you don't have to add anything to your program, at least not right now, and it'll tell you or at least give you some information. All right. So let's go back over here. If we did Valgrind on main, it ran the program. Notice it did take a lot longer. In use at exit 0 bytes and 0 blocks. That means this program used memory correctly, or at least Valgrind did not detect any errors, and it did not spit out any errors while it was running. The big caveat here is all heap blocks were freed, no leaks are possible. We'll go into what the heap means later, either next class or the one after. Yeah, just FYI, there's a lot of chicken and egg going on right now because I haven't explained to you what the heap is. But this tool is very helpful. All right, great. Well, that's nice. Can we come up with an error? Sure, let's see if we can come up with an error. All right, include IO stream, int argc star rv. Okay. So let's see. Int a equals new int of 100. Did y'all ever write this? You ever call new?
In object-oriented.
In object-oriented, but did you ever do it in C++?
No.
No. Okay. It means something a little different, although very similar. In OOP, when you did this, it was actually creating. Let me move this file to error.cpp. There. Now it highlights new. It is allocating exactly 100 integers on the heap. In Java, it was something different. It actually allocated an array object that would then manage 100 integers. But that's not what's happening here. It is creating exactly 100 integers on the heap. That's somewhere else in memory. We'll get to that shortly, next class. So we have 100 integers. We do for int I equals 0. I is less than or equal to 100, I plus plus, and then we can do a sub I equals I, and there we go. All right. Anyone see some problems with this code?
Yes.
Yeah.
What are some problems?
It's going to go to 101.
It's going to go to 100. Oh, the 101th element. All right, that's one problem. Anyone see the other one? There's two of them. All right, let's see if Valgrind will help us out. Hey, look, G++ compiled it, not a problem. A.out, it even ran. This is very important. There are two bugs in your program, memory bugs, actually serious memory bugs. G++ compiled it without warning and ran it without appearing to have a problem. That's going to happen. Even if your program runs and appears to run without a problem, does not mean it's correct. It just didn't happen to have a problem this time that it ran. I might be able to run this thing a million times without error, but it'll still have problems. Yes?
Is the bug that's never like deallocating the memory?
Yes. So the memory was never deallocated. That's correct. So we do Valgrind, A.out. Oh, here we go. Invalid write of size 4. Well, it's not really telling us, but says it's 0 bytes after a block of 400, and it says that it leaked exactly 400 bytes in one block. Huh, what are those 400 bytes?
That extra number? Or is it the whole number?
Sorry, couldn't hear you.
Is it the extra element? In the,
Okay, so the 0 bytes after block size of 400 is that 101th element.
Okay.
That's correct. Yes. Once this definitely lost 400 bytes.
That's all the other integers.
Right, so that's the integers. Why is it 400 bytes? What's that?
An integer is 4 bytes.
Correct. An integer in C++ is 4 bytes. All right. This was not too helpful. The reason for that is when I compiled it, I did not turn on debugging. Watch what happens when I turn on debugging and then run it under Valgrind. It actually says the error is error.cpp on line 7. Okay, that's a lot more helpful. It tells us exactly where that error is. So let's go up cpp, line 7. The error is right here. Well, that's because I is going too far, so let's go ahead and get rid of that equal sign. And then let's go ahead and recompile and then run it. All right, so we got rid of the writing error. I may have gone a little quick right there. Everyone saw what was going. Invalid write means you're writing past it. You could do invalid read as well, which means you're reading past it as well. It'll tell you both. But we still have this definitely lost 400 bytes. Well, that's that integer. And what we need to do is delete it. Yes?
Would free also work in that situation too?
I'm sorry, I didn't hear you. If we what?
Would the free command also work in that situation as well?
No. Good question. All right. New and delete have to be paired. Malloc and free have to be paired. Malloc and free are one type of memory allocation scheme. It is not guaranteed that new and delete and malloc and free are using the same memory allocator. They could be, but from my experience, they never are. So every new has to have a delete. Every malloc, it could be malloc, calloc, or realloc, has to have a free. But in C++, I'm going to try and stick with new and delete, even though I do actually prefer malloc and free. Great question. Any others? So notice here, in use is 0. Total, there are 2 allocations and 2 free. This number of bytes allocated. That's perfectly fine because we deallocate the memory afterwards. Valgrind's just saying, hey, look, you allocated this much memory. That's fine. No problems there. Unless you're consuming too much memory, then you can go and try and use Valgrind to investigate what's consuming all the memory. But we don't care about that, at least not right now. All right, I'm going to go open up error.cpp again, and I'm going to put these. Put the errors back in. That way, if someone wants to look at the code and watch Valgrind complain at you, there you are. All right. Oh, by the way, leak check full. Here's another thing I forgot to show you. If you turn on debugging, so you have to have debugging on, and you pass in leak check full, I think there was one other thing you had to pass. 400 bytes are definitely lost in a record of 1 and 1 operator new on error.cpp.4. So it is literally telling you that you did not deallocate what you allocated on error.cpp line 4. And of course, that's the new right here. So Valgrind can be very helpful on finding memory leaks. Now, for this class, I'm going to stick with Valgrind. There are other tools that actually are better than Valgrind, but the reason I'm going to stick with Valgrind is for this class, it should find everything that you care about, and it is definitely easier to use than the other programs. So we're just going to stick with Valgrind for this class. Okay, great. So I talked about that. Oh yeah, these numbers over here, you notice they keep changing. Every time your program runs, it's a process, and every process is given a unique identifier. That's a unique identifier. It doesn't really matter for this class. All right, so here we go. Ints new 1024. When I ran it here, 4096 bytes lost in one block, which meant that we did not free our memory. A better version, here we go, deletes it, and then Valgrind says that we did deallocate it, so I went through that, perfect. Here we go with another error, invalid write of size 4. In this situation, it did not tell us the line number. Where is it? Well, what we need to do is add debug flags -g, run it, and then this time it tells us it's in test.c line 7, which if we were to go back to this code, would be right there. This is basically the PowerPoint version of what I just did in class, just making sure I taught you everything, or showed you everything. Okay, so Valgrind can be used to detect memory leaks and memory access errors. Valgrind provides other tools to profile, but those are definitely beyond the scope. Notice that Java has memory debugging built in, but C++ doesn't. Why? Yes.
Is it because Java auto takes care of memory?
Right, so Java has garbage collection, and so yeah, it can automatically detect these problems and tell you if you're going beyond the bounds. That's correct. C++ doesn't do that though. Why doesn't C++ have a garbage collector? Maybe I should rephrase that. Why doesn't C++ have a garbage collector by default? Because you could use one. People have written garbage collect libraries for C++, and you could use it. But we're not using it in this class, and most people who program in C++ do not use one. Why?
That way you can kind of customize what memory you want to allocate, deallocate.
Okay. Yeah, there'd be certain situations where that would be the case, right? Yeah. There, especially if you're doing a device driver of some sort, you need to know the exact memory location where things are allocated, deallocated from. That, yes, that's correct. But that's the majority of time in C++. You're not doing a device driver. Good guess. Great guess. That was actually accurate. But there's a bigger reason why they don't do it. Yes.
It's slow.
It's slower. Yep. Garbage collection takes time to do. Every time your program's running, if there's a garbage collector, it just has to stop your program, run some garbage collection routine, manually deallocate things, do reference counting and all sorts of things, and that just slows down your machine substantially. If you ever go to, I think it was called the Great Language Shootout, where it compares languages, Java is always way slower than C or C++. Yeah, C and C++ always crush it, performance-wise. But that performance has a cost, because as you will find out in this class, taking care of memory yourself is pain and error prone. So it's a trade-off. It's not a win. If you're using a program that must have that performance, then yes, you'll probably want to use C++, which is why a lot of games are written in C++, or at least back in the day they were. Also, operating systems are written in C and C++, although that's for a different reason. But yeah, any questions about Valgrind? We will get to GNU plot later, which will show us how to nicely plot things out. You can use something besides GNU plot when we get to it if you really want to. I think there's what is it? Office probably has a couple of tools, but when I show you GNU plot, hopefully you'll see that I think it's a lot easier to use than other solutions. All right, any questions about this today? Man, we cruised through it. I must have missed something. All right.